Okay, let's start. Let's go on with the procedure of modeling. After giving you some general introduction about different types of models, we shall now go in more details. So we shall start discussing the elements of a model. Again, we are discussing in general modeling, but little by little we are framing our modeling description into the models of environmental systems. As we said, one of the characteristics of environmental system is the presence of a border. So conditions in which there is an inside stable and an outside unstable. So the system is described inside in terms of states by what we may call state variables, while the external environment is acting on the behavior of a system through what we may call external variables, or most often referred to as forcing functions. So when I am asking you which are the 5 elements of the ecological model or of environmental model, first of all, we shall list external variables or forcing functions. As an example, typically, the temperature is a control function that acts dramatically on the rate or the process rates of living systems. Then it is important to define variability ranges for the external functions, like, for example, as we will see when we will discuss the dependence on temperature of primary production processes. You will see that different ranges of temperature will act differently on the performance of ecological processes. So it is important to model or to describe the effects of temperatures in terms of variability ranges. The second element of the environmental systems are state variables. State variables may be dependent or independent. Independent state variables are basic variables, while dependent state variables are state variables that depend on a combination of independent state variables or external variables. As for the external variables, for state variables, it is important to establish or to define a range of variabilities. Then the third element is equations, mathematical equations. Mathematical equations link external variables and internal state variables. The fourth element is that of universal constants. Typically, these values are dependent only on the units you employ for measuring or for describing some processes. Typically, a universal constant is the speed of light. You know that in our universe, the speed of light is a constant whatsoever. And then the fifth fundamental element is that of parameters. Parameters are very important because are the elements on which we may act in order to modify the behaviors of the model. At different values of the parameters, you will have different behaviors of the model. And parameters are important in the phase of calibrations, because by changing a value of parameters, we change the behavior of the model. So it might be possible to make the behavior of a model more adherent to experimental data. Let's go on a little bit with model classification, so model types. We already introduced the distinction between research and management models. Research models are those employed for scientific investigation. management models are instead support applications for productive processes. We have already said that in general, management models are derivations of scientific models. Then there is another epistemological classification between deterministic and stochastic models. Deterministic models are those models that present a defined or exact output. Typically, a deterministic model, in a deterministic model, you may say the evolution of a state variable as a continuous function that it describes in an exact way the value of the various state variables. On the contrary, stochastic models are models for which you do not have an exact defined values of the state functions. Instead, output values are possibly described by probability distributions. So, from an epistemological point of view, it is important to distinguish between deterministic or Cartesian, if you want, models, and stochastic or chaotic or random models that present some kind of randomness. Then there is another important definition, classification between compartmental and matrix models. Compartmental models are models in which state variables are associated with time-dependent ordinary differential equations. So this means that we may identify some state variables that are associated to a specific compartment of your ecological model. By compartment, we may mean, for example, a species or a type of molecule, biological molecule. For example, organic nitrogen or inorganic nitrogen, these may be seen as compartments. Compartmental matrix are to be compared with matrix models. Matrix models are specific compartmental models in which the relationships between variables may be described by matrices. I anticipate that this kind of models are restrict models, types in which the relationships between state variables are linear. Another important distinction is that between reductionistic and holistic models. We have already seen the definition of these two terms. Reductionistic models include as much detail as possible. On the contrary, holistic models are based on principle of the maximum generality. As a rule of thumb, we may see reductionistic models as a mechanical, for example, mechanical description of a system that is undergoing only, for example, gravitational forces, and then thinking to, for example, the law of Newton laws of motions is an example of a reductionistic model. On the contrary, an holistic model is a model in which you employ general indicators that are derived from principle of a maximum generality, typically thermodynamic models in which you employ, for example, pressure, temperature, and volumes are holistic descriptions. Of course, there is the possibility of switching from reductionistic to holistic, and the tools from passing from reductionistic modeling to holistic model is normally statistical mechanics. So you start building a reductionistic model, then when the complication starts becoming very high, you introduce or you employ the tool of statistical mechanics, and then, as you may recall from your early physics course, there is a way of passing from the statistical mechanics description to the thermodynamic description, which is typically an holistic approach. It is also epistemologically important to distinguish between static and dynamic model. A static model is a model for which there is at least in which the state variables, do not all depend on times. So in a static model, you may define a static model by writing that derivative in time of the vector of state variables is always 0. A dynamic model is a model in which there is at least some state variables that depends on time. So there is some state variables for which the derivative in time is different from 0. Then from the special heterogeneity, we may also introduce the distinction between distributed and aggregated parameters models. Distributed parameters models are models in which parameters are function of time and position. Instead, aggregated parameters models are models in which parameters are constant, at least within certain spatial-temporal limits. We will see some examples of these different models later in the class. From the mathematical formulation point of view, we may distinguish two very general formulations: distributed parameters models and aggregated parameters models. Typically, distributed parameters models are models for which you may employ what we may call partial differential equations. Typical way of representing differential equation in a distributed parameter model is an equations which you consider derivatives on the different spatial coordinates, but also on the temporal coordinate. Typically, you may write that the variation in time of a certain state variable, I, and the variation in space of a certain state variable by combining by this differential equation is equal to a function of the space and of time. On the contrary, in aggregated parameters model, we employ ordinary differential equation instead of partial differential equation, partial derivative equation. Ordinary differential equations are equations in which appears only derivatives in times. So derivatives that may be of first, second, third, nth order of a state variable is equal to a function of time. So this is the general description of aggregated parameters models by ordinary differential equations. From the mathematical point of view, it is also very important to distinguish between linear and nonlinear models. Why this it is important? Because typically, linear models are described by first-order differential equations, while nonlinear models are models in which one or more equations are of higher order than the first. As you can imagine, the dream of a mathematical model or of environmental modeler is to have first-order differential equations, so linear models. Why this? Because as we will see soon, linear differential equations or first-order differential equations are equations that may present analytical solutions. So it is not always easy to find solution of differential equation, in particular, if differential equation is of a higher order than the first. It is very, very seldom that you will find a solution, an analytical solution. Instead, you should recall mathematical solutions. Mathematical solutions require very important computational capabilities, and it is not always possible to find a solution of nonlinear differential systems of equations. That's why we have a dream, or we would like to find linear models, so first order differential equations, for which, as we will see soon, we may have simple analytical solution, and so we wouldn't need very important computational capabilities in order to solve the system of differential equations. Then, from an epistemological point of view, it is also important the distinction between causal and black box model. Causal models are models in which there is an input-output state relationship. So that we may say that the input and the output state are linked by causal relationships. Again, this is a dream solution, a dream situation, meaning that in the reality, most models, especially in environmental modeling, are black box models, for which there is some kind of uncertainties in the input, but are directly reflected on the uncertainties on the output. Causal and black box models are two external representations. Causal models, you may always find detailed relationships between the input and the output. Black box models are models in which you really do not know which is the relationship between the input and the output. As a matter of fact, real ecological models or environmental models are in between causal and black box model, what we call gray box models. Gray box models are those models for which we may describe where we have knowledge about input and output relationships, for example, by identifying some kind of statistical relationship between the input and the output of the model, while some of the relationships are not understood or not explained at all. So then you may recall you should apply more sophisticated mathematical tools for linking input and output. Then a final differentiation or a final classification from a mathematical point of view is that what distinguishes between autonomous and non-autonomous model. Typically in autonomous models, differential equation does not depend explicitly on time. We may mathematically describe this by saying that the derivative in times of the state variable is simply a function of the state variable's vector, while non-autonomous systems, differential equation depends explicitly on time. So we may write that the derivative in time of a state variable vector is equal to a function not only of the values of the state variables, but also on time. So essentially, this means that the functions may vary in time for non-autonomous systems, while this function varies for autonomous systems. This function varies only as a function, depending on the values of the state vectors. Then there are the classification linked to the possibility of applying general principles to your model. For example, we may distinguish between demographic, energetic, and chemical models. In demographic model, there you may employ a general law that we may call it the conservation of information. Typically in demographic model, the variable are the number of individuals, and the information content is represented by the genome, so quantity of genetic information coded in each individual. While in case of energetic or chemical models, The conservation principles are, in the first case, the conservation of energy. So typically, the currency of an energetic models may be energy density, for example, joule per cubic meters, while in the case of conservation of mass, the currency of a model is described in terms of density of matter, for example, milligrams per liter. Typically, the environmental engineer is already comfortable with chemical models in which, for example, you may represent a state variable in terms of milligram of nitrogen in the form, for example, of nitrate per liter. This is the typical currency describing a conservation of mass chemical model. I have here introduced silently a new concept, the concept of a currency. The currency, it is what it is exchanged between the various compartments or elements that appear in the model. So currency may be energy, may be matter, may be number of individuals, and so on. Let's switch immediately to a first representation of linear models. We have seen that, or we have said that we might mostly try to build linear representation of my ecological systems or my environmental system. We may say, for example, that my environmental system is described by a state vector that is constituted by 4 elements, for example, x1, x2, x3, and x4. So these are the state variables that build up the state variables vector. So each one of these state variables describe one compartment. Please note that I am introducing here notation, the language. I'm just making more explicit the language, but for me it is already evident, and for you it might not be evident. So we may describe a linear model by, for example, introducing 4 compartments. You may recall that we have said that compartmental models are linked to matrix representation. We have already said that linear models are models for which we have first order derivative equations, differential equations. So we may represent the interactions between the compartment describing what's happening between your environmental systems by subdividing your environmental systems in compartments. In this example, I have introduced 4 compartments. Each compartment is described by a state variables, so that x1, x2, x3, and x4 made up the state variable vectors. So the vectors describing the state, holistic or comprehensive state of the system. Then how do we describe the dynamic of this model? We may say that each of these compartments may interact with other compartments through, for example, a flow. And we may introduce this description. This is a box and flow description, that is a very general description. We may describe interaction between the various state variables by introducing some arrows linking, for example, state variables 1 to state variables 3. Please note that these arrows are oriented arrows. This means that x1 is acting on x4, x1 is acting on x3, but x3 is not acting on x2, instead it is x2 that is acting on x3. By this representation, we may build a matrix that describe interactions between the elements of a model. In particular, we may say that element 1 interacts with element 1 itself. This is self-recycling by a flow that is described by the quantity A11. Element 1 is interacting with element 2 by a flow that is described by A12, and so on. So by the matrix representation, we may start implementing a dynamic representation of interactions between the compartments that build up our environmental systems. What is the advantage of using this matrix representation? The advantage, immediate trivial advantage, is that if we describe the states of the system by the vector xt, so this x is x1, x2, x3, and x4 at times t, so it is a vector. So if you multiply the algebra of matrices, the matrix representing interactions between these four elements, so this is a row by column product, you obtain the evolutions of the state vector, so the state of a system at times t plus 1 as a simple row by column product in the algebra of matrix A times the state vector x at time t. Is it clear? Do you have any question? So this is quite trivial. Please note that on the diagonal of interaction matrix, what we will subsequently call the adjacency matrix, we have self-recycling. So if there is a kind of interactions between x4 and x4 itself, we shall represent this interaction with an arrow that exits from the compartment and goes back to the compartment, and this arrow appears on the diagonal of a matrix. So a model in which there is no internal recycling in the compartment will display all 0 values on the diagonal. So now let's start to discuss the problem of selecting the appropriate model. How can we select the appropriate model? There are a series of guidelines that we shall discuss now. The appropriate model, the selection of the appropriate model depends on the problem in analysis. For example, if we have a neutrification problem, we will select a model that is able to describe at least the process of primary production, because you know that the primary production process is a key process in eutrification, in eutrophic situations. Then the target of a model is another important aspect that will guide you in the selection of the appropriate model. Again, for example, if your model is an eutrophication model in a shallow water body, then you shall employ, for example, a lake model in which you shall include all the relevant aspects of that may interact with the eutrophic process in the lake. For example, the interaction with sediments will be a key aspect of your shallow lake model, shallow eutrophic lake model. Then another important guideline in selecting a model is the complexity. We have already discussed about complexity. Complexity is a characteristics of living systems. Living systems are complex systems. In the really basic meaning of complexity word. What complexity means comes from the Latin complexum. Complexum means to embrace. So a complex model is, a complex system is a system that embraces several hierarchical levels. So a complex system is a system in which you may include elementary elements or more complex organisms, interaction with the surrounding environments, climatic effects, and so on. So the complexity is a characteristic of environmental systems, but as we will see soon, the complexity may also be seen as a characteristics of a model. There are different complex models that are more complex than others. You may increasing arbitrarily the complexity of a model. The problem is that as you increase the complexity of your model, you will need more important computing powers in order to solve your equation, your differential equations. So it is important to find an appropriate complexity, and the appropriate complexity of a model is exactly the complexity needed to deal with the complexity of the environmental system you want to describe. Another important guideline in selecting the appropriate model is the selection of appropriate temporal and spatial scales. Again, let's stay to the example of eutrophication. Eutrophication is typically a local phenomenon, and is a phenomenon that is linked to the sequence, to the seasonal sequence. So in terms of temporal scales, if your model is in a eutrophication model, the temporal scale should be that of seasons, at least. It is useless to describe in terms of minutes, for example, temporal scales of minutes. And in terms of spatial scales, the scales, for example, if it is a lake model, is that of some hundreds of meters. So you are not going to describe processes on the spatial scales of millimeters or centimeters. Instead, you will describe processes on the scale of meters, tenths of meter, or 10 meters, or maybe 100 meters, or hectares, and so on. So, temporal and spatial scales, required temporal and spatial scales is also a guideline in order to select the appropriate model. Another relevant criteria for selecting the appropriate model is that of the availability of data in terms of quantity and quality of the data. It is useless to build a model, for example, with a temporal scale of minutes if you have only one date per year, or for example, 4 dates per year, meaning 1 date per season. So the availability of data is another guideline that will guide you in the selection of the appropriate model. Then other epistemological guidelines are linked to the sophistication of your description. For example, structural dynamics models are models in which you try to include the structural variability or structural dynamicity of environmental systems. I recall you, structural variability means the onset of a flow. So, for example, the changement of a diet of an element, or for example, the extinction of an animal, of an organism. So this means the disparition of, for example, a state variable, or the appearance of invasive species or alien species. This means, from a structural dynamic point of view, the appearance of a new state variables and of a new set of flows. and so on. And then from the mathematical formulation point of view, also the possibility of building an object-oriented model for those of you that are comfortable with the C++, for example, that is an object-oriented programming language. Object-oriented models are models in which you may include in the definition of a single the definition of the single individuals, the way in which the individuals interact each other or interact with the surrounding environment. This is an object-oriented approach in which you include into the single individuals the way or the methods you employ by employing programming language terminology, the methods that these single individuals may employ to interact with the surrounding environment. So when you shall select the appropriate model, you should first of all ask yourself if you may formalize your model by matrices, and this is fantastic, but this is restricted by implying linear relations. So you know that if you have a non-linear relationship, like for example, it is the case when you include friction in your model, you may not use linear relationships, so you may not use a formalization by matrices. Then you may ask yourself if you may include some kind of stationarity into the model. And this is typically the case when your model is limited by the availability of data. Typically, stationary models provide averaged values, so averaged responsive, for example, seasonal values. You may include probabilistic modeling when you have limited availability of data, and in particular, if your knowledge is limited to clouds of probabilities instead of exact values. The opposite is that of including differential equations, if you can formalize all the interaction by differential equations. But please remember that in this case, you will need large amount of data with good quality, and you should be able to describe the evolution in time and space of the model. Of course, this is a Cartesian reductionistic detailed description that is formalized by differential equation. I may anticipate immediately that it is almost never the case when you deal with environmental system. Then you may wish to include structural dynamics. It's typically the case in which you want to study the evolution or evolving systems. Then please note that then you will need a large amount of data and possibly of good quality. Then again, if you may employ an object-oriented approach in which the elementary object in your model is the individual. So the individual is the base unit of your model. Do you have any question? Okay, now let's continue our description in terms of the selection of the appropriate model, in terms of selecting the model of an adequate complexity. You have to remember that a model is reliable as the least reliable of inputs, meaning that you should look for a reasonable compromise on the complexity of the different submodels. So it is useless that you include into your model a very complex or detailed description of some process if you, for example, do not have enough detailed description in terms of observation in the real systems of nature. Then you should look for the simple as possible model with the minimum required complexity. Simple as possible, so include as least as possible of elements, but please include all the needed elements in terms of the target or of the objective of your model. The objective of selecting an appropriate model is that of getting a better understanding of the system, not necessarily of a reliable and quantitative prediction. Instead, you would most likely have a model with the appropriate structure in terms of number of state variables, number of compartments, number of relationships describing the interactions between these objects. This is why you need a systemic approach. And this is why you need also to keep in mind that the model is not the reality, but instead an attempt to represent certain elements peculiar to the system. Again, the selection of a model has to do with the target, with the quantity of data, with the type of model, with the process you are going to include, and in particular with the objective of the model. Again, the example is that of a eutrophication model. If you want to build a eutrophication model, you cannot make without including, for example, algal concentration or chlorophyll A concentration into your model. That is a proxy or an indicator of eutrophicity or eutrophic processes at play into your model. The subsequent lectures will describe in detail the procedure to build a model. The procedure to build the model is represented by this schema, this flow chart. We start by problem definition, then model conceptualizations, mathematical formulation, verification of your mathematical formulation, numerical formulation, that means translating mathematical formulation into numerical equations, sensitivity analysis, so studying the behavior of your model, calibration, so changing your model, and validation of your model. We'll describe all these 8 processes in detail in the next lectures. Problem definitions means what is the problem, which are the data, so problem and data analysis. This is the time in which you choose the limits in terms of spatial and temporal scales. You identify subsystems, you define the hierarchical level at which your description applies. Once you have defined a problem definition, you start with model conceptualization. Model conceptualization is a very key point in which you start building your model. You identify, for example, which are the external elements that act on your model. For example, forcing function. Should I include temperature? Should I include pressure? Should I include, for example, fishery into my model? Should I include, for example, fertilizations in my model and so on? Then this is the time in which you identify state variables. So I shall include, for example, chlorophyll A, or nitrogen in the form of nitrate, or phosphorus in the form of phosphate, or, for example, other concentration of elements that may be toxic for the living organisms. You start identifying functional relationships. For example, temperature may act on primary production by changing the rate at which living algae replicates themselves, the typical identification of a functional relationship. Then you start designing conceptual diagrams. So conceptual diagrams mean, for example, writing box and flows or compartmental subdivision of the system. So you may say, okay, one state variable may be, for example, chlorophyll A because I need a description of the primary production processes and so on. And then this is the point at which you start identify and measuring, as we will see in the next lecture, the complexity of your model. I recall you the complexity of your model should be consistent with the complexity that you may foresee for the system that you want to describe. Once you have a model conceptualization, you are ready to start the mathematical formulation phase, in which you write explicitly equations for each relationships, the relationships that you have identified in the preceding phase. Then this is the point in which you identify constants and parameters. I recall you that universal constants depends on the units that you employed for describing the quantities that appear into your model. So you identify constant and parameters. Identify also the range of variability of the parameters. So the parameters that you include into your model, for example, a parameter may be the production rate of chlorophyll or the number of cells, number of phytoplankton cells produced per unit time. So it is a production rate. So you shall identify a reasonable range of variability for the parameter, and then this is the time in which you define the mathematical formalism, so ordinary differential equation, partial derivative equation, and so on. Once you have mathematically formalized, you are ready for verification. So you start resolving equations, and you start analyzing the behavior of the model. For example, you shall verify that your equations are consistent with your understanding of the biological functioning of a system. For example, one trivial verification might be that of studying the changing of the behavior of your model with temperature. For example, if dissolved oxygen is one state variable in your model, this is the point in which you shall verify that dissolved oxygen depends on the temperature in a way such as if the temperature increases, you expect dissolved oxygen to decrease. If this does not happen, this is meaning that you have forget or you're not correctly describing your system. Once you have done verification, you're ready for formalizing numerically your model. And this is the point at which you choose the programming language and software. Typically, now you translate your mathematical equation into a numerical environment, what may be, for example, MATLAB or some other programming language. You may write C++ code, or you may write JavaScript or Java code describing mathematically your formalized equations. So now you're ready to play with your model, and you pass to the next step, that is that of sensitivity analysis. What does it mean doing sensitivity analysis? It means that you have a numerically formulated model, so you have already a calculation environment. So you start playing with the parameters and forcing function values. So you start to understand or to study how changing parameters or values of external variables changes the behavior of your model. So you change parameters, change external variable, and analyze the results in terms of the changement of the behavior of your model. Sensitivity analysis, it is a prerequisite in order to switch to the next step, that is that of calibration. During calibration, you employ your numerical environment to resolve your systems of differential equations, and you start doing a comparison with experimental data. During this comparison with experimental data, you may find that your model is not behaving appropriately to your considering your knowledge of the behavior of the system. So this is the time in which you may change the value of the parameter, finding optimum values of the parameter in order to make the behavior of your model the most adherent as possible to the observed system. And once you have ended with calibration, you are ready for validating your model. The validation of your models means applying a calibrated model into a system that is different, at least statistically speaking, from the system employed with calibration. You need a validated model if you want your model to be, for example, a commercial tool. Model like, for example, ModFlow, that is the model describing groundwater interaction that is developed by the Danish Hydraulic Institute, the Mcsa, is a validated model so that you can, your description is validated and you can employ this tool. This model becomes really a research tool that may be employed to describe and to study or to do research or to analyze systems that even are not was employed for calibration. Once you have your model working, you shall pose yourself some questions like, for example, is the model stable? It may happen, for example, it may happen, but this is often the case when dealing with environmental systems model, but one state variable in your model, after a certain initial transient time, starts derivating in a catastrophic and dramatic way, meaning, for example, that your state variable is constant up to a point when it becomes deviating dramatically from the behavior. You see, for example, state, let's see if I can draw you an example of this. Is the model stable? The state variable is like that. Is the model unstable? The state variable may behave like that. So you have a dramatic deviation. Does the model respond as I expect? This is an important check because this ensures that you have included into your model all your understanding of the behavior of the system. Like, for example, like the example I gave you before of dissolved oxygen concentration, I am expecting that the model should respond to variation on control function, like, for example, the temperature, with an appropriate variation on the state variables that depend dramatically on this control variable. So, for example, the oxygen dissolved concentration should decrease with increasing temperature. Another example, for example, is that of a primary production model, in which I am expecting that if the nutrients for the organism that you are modeling increases, then you may expect that the organism also increases as well. So, for example, if nitrogen increases in your lake model, then you expect that algal growth increases as well. And then a last check is that of checking if a mathematical formulation is consistent in terms of units, so currencies of descriptions of the elements that appear into your system, but also the formal correctness of the equation implemented into your model is another important aspect to be included. Okay, by now I stop here today, and we will continue by going into the details of the modeling procedure on next Thursday. Do you have any questions? Okay, I stay a little bit more in the class, but then I will exit soon from the class if you do not have any questions.